Hello, this is Math Kimchi, and in this video we will look at summation, and this is part 2. And in this part we will be looking at the sums of finite and infinite geometric sequences, and also create a program to basically recap everything we learned so far. So first, let's look at the summations of geometric sequences. And this time I will be using Sn to represent the sum of the first n terms of a geometric sequence, whereas last time we used the summation notation. But they're basically the same thing. And this entire thing, if you were to write it in a more mathematical way, it's basically just saying this, and unlike last time, we will be starting at the first term and end on the nth term. But last time we could start wherever and also end wherever. But if we were to have to start on, for example, the mth term, then we can just say that the nth term was the first term and kind of subtract to calculate the new n. But anyways, we're trying to find what Sn equals to, and this is what we're trying to find. So let's just write all of that out, and there's nothing too weird so far, and we're just going from I is equal to 1 to I is equal to n, and then now we take out the a1 from all of the right hand terms, and then we can divide by a1 because we know that it's one of the rules for geometric sequences to not be that none of the terms can be 0, so that includes the first term. And two additional kind of rules for geometric sequences is that r can't be 1 or 0. And anyways, we're allowed to divide both sides by a1 because we know if this is a geometric sequence, then a1 is not allowed to be 0. And so now we're going to group everything from here to here, everything on the right side except for the very first term, and we're just going to be grouping it using parentheses. And the reason why I'm leaving this still up here is because it's going to be important later in the proof. And so now that we grouped everything, we can take out r from all of these terms, and to do that we just subtract 1 from all of the exponents. And so now we can add 0 to the entire thing, and r to the n minus 1 minus r to the n minus 1 just equals to 0, because these two are the same things and it just cancels out. And now we can just calculate this by saying that it is equal to 1 minus 1, because 2 minus 1 minus 1 is 0, and this is just 0 as well. And now you might notice something kind of interesting, and it's going to be more obvious if we take out this term and we're just multiplying it by r, because we're multiplying everything in here by r, and this becomes r to the n. And now we can also calculate this. It's just r to the 0, and that's just going to be 1. And now we just move this term to the front, I guess. And now we can notice something very interesting. So this is just the next term. And we notice that everything in here is equal to Sn divided by A1. And so what we can do is just replace everything in here by Sn over A1, because we know that this is equal to this, which is equal to this. And so now we can just use basic algebra to solve for Sn. So, and we can get rid of this because we don't need that anymore. And we just subtract both sides by r times Sn over A1. And we can factor this out, and we get 1 minus r times Sn over A1 is equal to 1 minus r to the n. And after some more algebra, we get that Sn is equal to A1 times 1 minus r to the n all over 1 minus r. And that's the formula for a geometric sequence, or the sum of a geometric sequence. And now we can look at the summation of an infinite geometric sequence. And what we have here is what we had last time, except it goes on for infinity. And you might be thinking, well, isn't that just going to be infinity? Well, if r was greater than 1, then it might be, but when we have an infinite geometric sequence and take the sum of that, we're kind of assuming that r is less than 1, and also that r is greater than -1, and that's not actually equal to infinity. And if you don't believe me, something you can try is adding 1/2 by 1/4 by 1/8, and just keep on adding it and dividing by 2, and you'll see that as you keep on adding, you're getting closer and closer to the number 1, and it actually never exceeds 1 and only gets closer and closer to 1. So that's something pretty cool, and this will kind of show why that is. And so first we can factor out the A1 like last time and divide, or before we divide, we can just calculate all the exponents. And now we can divide by A1, and we're gonna leave this up here because it's gonna be important later. And we can just group everything here except for the very first term, and we can take out the r from everything in here, and we can notice that this is equal to this, and this is equal to this, and this will be equal to whatever's here, and that just goes on until, well, that goes on forever. And so we can say that it's just equal to s over a1, and now we can just solve everything using simple algebra. And this is the formula we get to calculate the sum of an infinite geometric sequence. And something interesting is this kind of fits with this formula, because, well, if r is less than 1 but greater than -1, and you take that to infinity, it's basically going to be equal to 0. And so we have s is equal to a1 minus r to the infinity, which is equal to 0 over 1 minus r. And this is just going to be 1 minus 0 equals 1. And so we have s equals a1 over 1 minus r. And we can see that this formula agrees with that, which I think is pretty interesting.